Okay, my name is Katrina Limbeck, and today I want to present our most recent work on geometry over edge pooling for graph neural networks. This is a shared project between the Eidos Lab at the University of Freiburg and Helmholtz Munich, as well as Guy Wolf's group at Milan at the University of Montreal. And to get started, the main motivation of graph pooling is to reduce the size of graphs during GNN training. They are usually used after and before convolutional layers in a graph neural network, and they aim to allow the GNN to learn from the graph's course in geometry. By reducing the size of graphs, useful pooling layers should preserve graph structure and topology. They should preserve task performance or even improve performance at downstream tasks. They should ensure computation efficiency, and they should preserve expressivity in the pooling operation. Motivated by these goals, in our paper, we are proposing two novel geometry over edge contraction-based pooling methods, namely mag edge pool and spread edge pool. And in order to motivate why we even propose new pooling layers, let's have a look at examples of different pool graphs. Specifically, we aim to respect original graph's geometry with our pooling choices, and to do so, we choose to do edge contraction pooling. So our own methods simply collapse adjacent nodes in the original graph, and by doing so, we do a very good job at preserving the original graph's connectivities and its overall geometry. However, this is not necessarily the case for other pooling methods. So it turns out that a lot of existing graph pooling methods actually struggle with preserving the graph structure and tend to destroy graph structures to varying extents. So here, for example, we see that there's a whole group of node dropping based pooling methods that remove nodes during training, and these tend to disconnect the graphs and remove key node information. There's another group of methods that also take a node-centric approach that cluster nodes into supernodes during pooling, and by doing so, they tend to create counterintuitive connectivities between the merged supernodes. Or they tend to return dense graph representations that don't really preserve any of the inherent sparsity or geometry or connectivities in the original graphs. So motivated by this comparison, we see that there's a need for more geometry-aware and structure-preserving graph pooling. Specifically, we'd like to make clear and interpretable pooling choices on which parts of the graph to preserve. And to do that, we decide to not only use edge contraction pooling, but to contract edges in a manner that preserves the graph structure and preserves its structural diversity. What it means is that in practice, we compute a graph structure diversity using either its magnitude or spread, and these geometric measures then allow us to define an importance score for every edge in a graph. So basically, this idea of structure diversity lets us compute how structurally relevant or redundant the edges in a graph are. And for edge contraction pooling, we then decide to contract the edges that are least important for the graph's overall structure first. So by doing this, in the end, we get a coarsened graph that preserves the graph's overall geometry, but has collapsed any redundant structures in the original graph. And then, in order to use this edge selection during training, what we do with the node features is that we aggregate them. So we can simply average the node features of the merged nodes after the pooling layer, and by doing so, we've defined a fully fledged pooling operation that we can flexibly use in any GNN architecture. Okay, so we fulfilled our main goal of defining a geometric objective on how to contract the edges in a graph. And let's now go on and consider whether this is actually a useful pooling operation. Specifically, if you're not yet convinced that this is a good idea, we compare our pooling method to other pooling layers across multiple tasks. And we first look at graph classification regression performance, where we find that our pooling methods reach the highest performance scores and the highest mean ranks across tasks. We also see that our pooling methods retain this high performance across varying pooling ratios and allow for a flexible choice of pooling ratio. Further, they do best at graph structure preservation in terms of preserving both spectral properties of the graphs as well as their geometric structure. And we've thus confirmed our original goal that our methods actually do well at structure-aware graph pooling. Finally, our methods also allow for more efficient GNN training compared to trainable pooling methods, and they fulfill certain theoretical guarantees to do with expressivity and isometry invariance. So, as a brief summary, in our paper we propose two novel edge contraction-based pooling methods that aim to preserve a graph's overall structure and its overall geometry. And if you want to learn more about our pooling methods, please check out our paper and our code.